All right, let's look at the chemical reaction rates in catalysts. So we're going to take a conceptual view of the speed at which chemical reactions happen and what makes that speed change and what can affect how quickly the reaction happens. So first of all, we have to think about what makes a chemical reaction even happen in the first place. And that collision model is the idea that particles must collide with enough energy for it to happen. So there is a picture on the note handout that shows that molecules bumping into each other, and it only works if they have enough energy and if they have the right orientation. If they're lined up the right way, when they bump into each other, they can react. If they're not lined up the right way, or if they don't have enough energy, or maybe both are not true, then they just bounce off each other and keep on bouncing around. So if those things are true, and make sure you know this for the test, if they have enough energy and the right orientation, they will be able to react. So that's what it takes to make a chemical reaction happen. Now, the energy is called activation energy. That energy that you need, activation energy is that minimum amount of energy needed to make the reaction happen. Some will have more than that amount, some will have just that amount, some will have less. The ones that have less will not be able to react. So activation energy is shown in these graphs right here. It's the energy necessary to get the reaction going and then make it turn into products. It doesn't matter if it's endothermic right here or exothermic, you're going to see a need for a starting energy. And this is something that we all know, like gasoline's highly flammable, but it won't burn without a spark. That spark is the activation energy. Or a match is highly flammable, but it won't burn until you strike it on something. That is the activation energy. So a chemical reaction then will go at a certain rate, of course. Chemical reactions will happen at a certain speed, and you can affect that speed with certain things like temperature. If you raise the temperature, the reaction will happen faster. Lower temperature, reaction happens slower. Probably the most obvious example is food. We all know not to leave food out for too long, especially, well, I should say the kind that needs to be refrigerated. We know it'll go bad. Imagine like meat or certain kinds of vegetables or dairy products or fish or whatever. Like if you leave them out in the sun for too long, they'll go bad because higher temperature allow the bacteria that are in there to do their chemical reactions faster that lead toward breaking down the proteins and things in those materials and then producing toxic things that would get you sick. On the other hand, a lower temperature thing means all the bacteria that are all over your food, and yes, your food is covered in bacteria, when you put it in the fridge, you're lowering the temperature, which slows down all the chemical reactions, including the chemical reactions of the bacteria living on your food, to the point where they produce their chemicals that are toxic so much more slowly that it's a long time before they build it to the point that it's not safe to eat them. So that means it extends the shelf life to keep the food cold because you're slowing down all the chemical reactions involved with its decay. Food is decaying all the time. You're just slowing it down by putting it in the fridge. Even more if you put it in the freezer. But it never stops. Even frozen food will eventually go bad. So anyway, it's just all this does is just speed the reaction up. If you warm it up, or slow the reaction down if you cool it down. Any chemical reaction, really. Now, aside from that, surface area can change things a lot too. Imagine, and this gives the example of like magnesium. A big chunk of magnesium, if you put it in acid, the acid can only react with the pieces that are magnesium and they're on the outside. Whereas if you grind it up into a powder, now these atoms that were in the middle and were hidden before are now all able to access the other chemical at once, and they can react all at once. It's really important to understand if you have 5 grams of chunk and 5 grams of powder, you will get the exact same amount of product. But the difference is you will get the product much faster out of the powder than you will out of the chunk. Even though they'll make the exact same number of grams of hydrogen in the end, this one will be far faster than this one. In the case of magnesium reacting with acid to make hydrogen gas. All right, now other examples of surface area and reaction rate. This includes all kinds of interesting things, and this is an animation of a collapsing grain silo, and I can actually do like this to make it a little easier to see. As it collapses, all that grain goes airborne, particularly like the dust, the wheat dust. It's been finely ground. So really, I should probably be calling this flour. But once it gets airborne, the spark sets it off. Like that's a truck. So we're talking like a person only being about this tall. That can set off an explosion. So that's you can see like the explosion happening. Okay, so that's part of the idea right there of, yeah, we know that flour isn't exactly explosive, but that's under normal conditions. You get it like this, yes, it can be explosive. And not just fire, even things like coffee creamery. You blast coffee creamer, that powder stuff, into the air and give it a good spark, you get something that looks like this. Looks like a blowtorch going, okay? So with enough surface area, stuff that even we don't even think is flammable can become very flammable. As you can see right there, I'm just letting it play again so the viewer can get a little bit of an appreciation for what's being shown here. Like, that's like a 60-foot tall fireball, or probably even more than that. Anyway, dust explosion. Simple dust. I'm not sure exactly what the setting is, but you can see dust is not explosive, but give it a spark and give it, like, get it airborne, oops, with lots of surface area and a proper ignition source, and that will happen. Or even sawdust. Look at what you can do with sawdust. All right, now, aside from those considerations, we have to also consider how else can we speed it? What else can we do to affect a reaction? So you can change the surface area. You can change the temperature. What else can we do to change a reaction? We can also add a catalyst. So we want to speed up the chemical reaction by lowering the activation energy needed. So this is the activation energy you need to put in for a regular reaction. This represents the lower activation energy with a catalyst. The reason why it does that is back to that idea of the atoms and molecules have to be arranged just the right way. They have to have the right orientation and the right energy. What a catalyst does, particularly a natural like an enzyme, it grabs those atoms and it holds them in the right position so that it can kind of put them together in just the right way. So instead of randomly bouncing, it's holding them the right way and allowing them to come together the right way, which means a lot less energy is needed to make the reaction happen. So because it's just kind of like grabbing those atoms and helping them come together in just the right way, it's not used up. It's not part of the reaction, which means if 1 gram of catalyst goes in, 1 gram of catalyst is left over at the end. None of it should be destroyed in the reaction, at least in theory. Now, in real life, there are things that can happen. Maybe you can make a product that then goes back and destroys the catalyst, but in theory, at least, a catalyst is neither consumed nor created during a reaction. So this little note right here, yeah, with catalyst, without catalyst. And probably the most immediate idea I can think of is like food. When you eat a Cheeto, it's the same chemical reaction as if you set it on fire. A Cheeto can react with oxygen to make carbon dioxide and water. That's setting it on fire. That's also the reaction when you digest it. But in order to set it on fire, you have to heat it to like, what, 700 degrees compared to you can digest it at like 37 degrees Celsius instead of like 700. So the reason you can digest a Cheeto without having to set yourself on fire is because you have enzymes that lower the activation energy, so you only have to be 37 degrees Celsius instead of like 700. So enzymes are natural catalysts, and this is what I was just saying it allows you to digest stuff at body temperature instead of like setting yourself on fire. And there are many kinds of enzymes, but they all do the same thing. They allow a reaction to happen more easily at just regular body temperature instead of some much higher temperature. So no matter whether it digests sugar or breaks down hydrogen peroxide and water and oxygen gas, this is a toxic byproduct of breathing oxygen, so you basically this enzyme makes it safe, or breaking down lactose so that you don't get sick from drinking milk products. These things, they all do the same thing. They lower the activation energy to make the reaction happen more quickly and easily. So even in a car, the catalytic converter does the exact same thing. It is a catalyst that allows these rather toxic gases to be turned into something less harmful. So see, that should take care of it.